Okay, so the next part that we have here is I don't know what we did last. Okay, so going back basically to calculus to chapter 13, I think we were in chapter 13, and so there's a part over there that talks about limits of trigonometric functions. And this part is of course important, so you need to pay attention to this part. I had to read this part once so I could really understand it, so I could basically explain it. Otherwise I couldn't explain it the first time really. Now the limits of trigonometric functions. Trigonometric functions. So what that is, so what we have over here, first we have a couple of theorems, and these theorems are generally about all functions, but they can be used in order to talk about trigonometric functions and finding the limits of trigonometric functions. So there is this theorem over here, which is theorem 3, that says that f and g be two real valued functions. Let f and g be two real valued functions. And now you understand what it means to be a real valued function. That means that the range of the function is the set of real numbers or some subset of the real numbers. And well, of course, that I mean, even if you know that much about the function, that's I mean, good information to have, because you at least know, for example, that probably your solution is not in the imaginary numbers. So let f and g be two real valued functions with the same domain, with the same domain such that f of g is less than or equal to f of x is less than or equal to g of x. F of x is less than or equal to g of x for all x in the domain of definition. For all x in the domain of definition. In the domain of definition. Okay. For some a, if the limit of f of x, the limit of f of x when x tends to a, and the limit of g of x when x tends to a exist, if both of these limits exist, then you can say that, then based on the information that you have here, then you can say that if these two limits exist, then you can say that the limit of f of x when x tends to a is less than or equal to the limit of g of x when x tends to a. So and this is illustrated this way here. So let's say that you have these two functions over here, and suppose you have, for example, let me draw this line over here, and let me draw this function this way. And let me draw this function another way, for example, another function, something like this. Okay. Now this function is y is equal to f of x, and this function over here is y is equal to g of x. And we said that basically f of x is less than or equal to g of x for all x in the definition for all x in the domain of the definition, meaning that for all x, basically wherever x happens to be defined in the case of those two functions, and those two functions having the same domain basically. So wherever x happens to be defined, the value of f of x is always less than or equal to the value of g of x. You can see what happens here. Is always less than or equal to g of x. For example, at this point, you can say that f of x and g of x have the same value. Otherwise, there is no point where f of x the value of f of x is greater than the value of g of x. Now, if that's the case, then for some value of a, if the limit of f of x at when x tends to a, and the limit of g of x when x tends to a, if that limit exists, then if these two limits exist, then the limit of f of x when x tends to a is also going to be less than or equal to the limit of g of x when x tends to a. And this has been called nothing, just the theorem 3. Okay. Okay, so the next theorem that we have here is called basically the next theorem is Theorem 4, which is also something useful in the case of finding the limits of trigonometric functions, and that is called the sandwich theorem. Theorem number 4, which is called the sandwich theorem. And what that is that let f, g, and h be real functions. Let f, g, and h be real functions, such that, so basically when we say real functions, what that means is that the domain and the range of the functions are basically are either the set of real numbers or a subset of real numbers, such that f of x is less than or equal to g of x is less than or equal to h of x for all x in the common domain of definition. For all x in the common domain of the definition. For some real number a, for some real number a, if the limit of f of x when x tends to a, if the limit of f of x when x tends to a is equal to L is equal to the limit of h of x when x tends to a. So for some real number a, if the limit of f of x when x tends to a is equal to L is equal to the limit of h of x when x tends to a, then since g of x is between f of x and h of x, the value of g of x was between f of x and h of x, then you can say that the limit of g of x when x tends to a is equal to L, and that is illustrated here. So you have basically these basically the y-axis and the x-axis, and let's say that this is the value of a that we were talking about, and let's say that you have this is the function, for example, y is equal to h of x, and suppose that, for example, you have this function over here is y is equal to g of x, and suppose that, for example, over here you have y is equal to f of x. So we said that the f of x is less than or equal to g of x is less than or equal to h of x for all x in the common domain of the definition. Now for some real number a, we said that for some real number a, if the limit of f of x when x tends to a is equal to the limit of h of x, so the limit of f of x when x tends to a is equal to the limit of h of x when x tends to a. Okay, so we said that if for some real number a if the limit of f of x is equal to limit of h of x is equal to L, then since this function was sandwiched between the two functions, then of course, well, not of course, I mean, you cannot just make this, I mean, come to the conclusion that since this function was sandwiched between the two functions, you can expect that the limit of g of x as x tends to a is equal to L, the same value. But of course you would have to prove this, and the proof has not been given here, and we are just taking this as it is. We are not proving it, but we can use it, and we are assuming that they have proved it, and the theorem has no problem. So that is basically, these are two theorems that we can use in order to do the rest of our work. Now there is an inequality relating the functions cos of x and sine of x, and that is basically you can say that cos of x is less than sine of x by x is less than 1. You can say that cos of x is less than sine of x by x is less than 1. And for 0 is less than the absolute value of x is less than pi by 2. That means that whether x is negative, that means that whether x is basically goes to all the way up to negative pi by 2 or positive pi by 2, this is going to be I mean, you can have values, basically you can have these values. If you take this as 0, then this becomes pi by 2 and this becomes negative pi by 2, and so you can go this way all the way up to pi by 2 but less than pi by 2, and then can come this way and all the way up to negative pi by 2, and that all of these angles are included in this inequality. And so for these x's, then you can always say that the cos of x is less than sine of x by x is less than 1. Now the way that you can prove this, I'm going to just write everything based on the proof, because the proof is a little bit, it's of course very simple, but I need to follow those steps in order to get to the conclusion. So basically we said that, you know that basically sine of negative x is equal to negative sine x. And you know that cos of negative x is equal to cos x. So what that means is that you need to, it's sufficient to prove the inequality. So you can say hence it is sufficient to prove the inequality for, it's sufficient to prove the inequality for 0 is less than x less than pi by 2. Meaning that if you prove the inequality for x is greater than 0 less than pi by 2, then over here you have since sine of negative x is equal to negative sine x, then over here basically, for example, in this part over here, so over here I have cos x is less than sine x by x, and over here I have 1. So the 1 is a constant, doesn't change. But suppose that I put x is equal to negative x in this inequality, I'll get cos of negative x less than sine of negative x over sine of negative x over negative x less than 1. And then again basically cos of negative x is equal to cos x, and that would be negative sine x by negative x less than 1, and then you can cancel these two out. You'll get cos of x is less than sine of x by x is less than 1. That means that if you prove this part, then you have already proved that for negative x as well. So what that means is that then if you prove the inequality for x between 0 and pi by 2, then you have proved that for negative x's as well, meaning going from 0 to negative pi by 2. So it's sufficient to prove the inequality for this inequality. So then what that means is that, let me draw a circle over here first. So if I have a circle over here, go and select the border 1, and so if you have a circle over here, let's draw, for example, this radius over here. I will draw some angle x over here, and I will draw this perpendicular, and then I will draw this perpendicular from here. I will connect these 2 points, and I call this point O, I call this point A, I call this point D, I call this point C, and I call this point B, and I call this angle X, I call this angle X, and that's basically all that we need here. Now, so this is remember that this is a unit circle, meaning OA is basically, the length of OA is equal to 1 unit. So now in this figure, O is the center of the unit circle, such that the angle AOC, this angle, the angle AOC is X radians. Angle AOC is equal to X radians, and X is less than 0, basically X is greater than 0 and less than pi by 2. That's basically our construction. Now the line segments BA, this line segment, and the line segment CD are perpendicular to OA. These two are perpendicular by construction. Now you can also join, for example, line AC as well, and then you can, based on the construction and all this, the situation over here, you can write the area of triangle OAC. Okay, so now based on this situation, what I can write is that the area of triangle OAC, which is OAC, this triangle over here, area of triangle OAC is less than the area of the sector OAC. Area of sector OAC is less than the sector OAC, is basically OA and coming along this curved line to C. So the area of the triangle is of course less than the area of the sector, and that is less than the area of triangle OAB. Triangle OAB is this big triangle over here. So area of triangle OAB. So now if the area of triangle OAC is basically 1/2 of the base times the height. So that is 1/2 of the base, which is OA, times CD. That is less than the area of the sector OAC. The area of sector OAC, since this angle is in radians, so the area of this sector is going to be some fraction of the area of the whole circle. The area of a full circle, area of a circle or a full circle is pi r squared. Pi r squared. Now this sector of the circle is basically X. You can basically, now a full circle is basically 2 pi by 2 pi, meaning that you can write 2 pi by 2 pi. So if you go basically one full revolution around the circle, that would be 2 pi, and 2 pi is one complete revolution, right? So this ratio would be 1, and then if you multiply it by pi r squared, that would be the area of a full circle. Now suppose that, and 2 pi is basically also the one complete revolution, or one complete revolution in terms of radian, and a complete full revolution in terms of radian, or one angle, a 2 pi radian angle that you go around the circle. Now X is X, this angle over here is X radians. So then if you write this as, instead of 2 pi, if you write X divided by 2 pi, then that's going to give you basically a fraction of a circle in terms of these two angles, the angle X and angle 2 pi, which is one complete revolution. And then this is area of a complete circle, and so this will give you the area of a fraction of a circle identified by this fraction over here. Now if x is basically equal to 2 pi, then that's one complete revolution to one complete revolution. That gives you 1, and you will get pi r squared, which is a full circle. Suppose that x is equal to pi radians, and pi divided by 2 pi times pi r squared, that gives you basically 1/2 of the area of a complete circle, and pi is basically this angle over here, so that would be half a circle. If x is equal to pi by 2, then that will give you the area of 1/4 of a circle, and so on and so forth. That's basically how you find the area of a sector in a circle. Basically, they use this fraction and multiply it by the area of the complete circle. So now what that means is that the area of this sector OAC is x divided by 2 pi times pi r squared. So and pi you can cancel out. You will get this as x divided by 2 pi, x divided by 2, and let me simplify this a little bit. So r squared is basically OA squared. R squared is basically OA squared. So instead of r squared, I can write OA squared. And so I can write this as OA squared times x divided by 2. So I can write this as basically OA squared times x, OA squared times x divided by 2. That is going to be the area of this sector. And then the area of this triangle OAB is 1/2 of the base times the height. So that is 1/2 of the base, which is OA, times the height, which is AB. Now I can simplify OA. Now of course you need to be careful here. Meaning that, for example, if you had an equation, for example, 1/2 of OA times CD is equal to, for example, OA squared, for example, OA squared times x divided by 2, for example. So then in this case, of course, you would, for example, if you multiplied, for example, both sides of this equation by 2, you would get, these two would cancel out, and you would get OA times CD. Okay, so then, for example, 2 and 2 would cancel out. Now, for example, let's say that you have suppose that, for example, OA is a negative value. So, for example, suppose that OA is for example, let's say that this OA is equal to negative. Well, this is not a good example. I'm sorry, I don't want to. This is not a good example, but over here in the inequality, when you, for example, when you multiply, for example, if you multiply every part in this inequality by 2, since 2 is a positive number, the direction of these inequality signs is not going to change. Otherwise, if you had, for example, 2a is less than, for example, 3b, then or negative 2a is less than negative 3b. Now, or let's say that, for example, this was this way, for example. So 2a is less than negative 3b, for example. A and b, for example, positive values. Now, if I multiply this inequality by a negative 1, what I would get is negative 2a is greater than positive 3b. Meaning that when you multiply an inequality with a negative 1, your basically this sign over here, which is less than, becomes greater than. So you need to be careful about that. Now what I want to do here is that I want to multiply every side of this, or every part of this inequality, by positive 2, so that these 2's will cancel out. So since 2 is a positive number, I can simply write OA times CD is less than basically OA squared times X is less than, for example, OA times AB. And again, since OA is a positive value, it's a length, it's a positive value, I can divide by OA as well. So dividing by OA, I'll get CD is less than OA times X is less than AB, for example. Now, so this is one equation that we can use later. Now, from this triangle OCD, let me write this over here. So from this triangle OCD, the sine of this angle, sine X, is basically equal to CD divided by OC. CD divided by OC. And because basically the sine of an angle is opposite by hypotenuse, so CD by OC. And since this is the radius of the circle is equal to OA, so I can write this as CD divided by OA. CD divided by OA. And hence you can write CD. You can write CD is equal to OA times sine X. OA times sine X. So that is again one thing. And again, tan of the angle X is equal to basically the opposite side by the adjacent side. So it would be, or you can think of this as, for example, the sine of angle X, and you can take these two sides, because the tan of an angle is nothing, is just simply a ratio. You can take the X in this triangle OCD, or you can take it in this triangle OBA, for example. So then you can, if you take your X in this triangle OBA, then you can write tan of X is equal to BA to OA, or AB to OA. AB to OA. And hence AB is equal to OA tan of X. OA tan of X. So then I can use this as well, and I can use this as well. So now what we found over here was that CD, which is OA sine X, is less than OA times X, is less than AB, which is equal to OA tan X. And again, since OA is a positive value, I can divide by OA, not changing the direction of these. So I'll get sine X is less than tan X, dividing by OA here. And so Now you need to basically, again, you need to be very careful when you do this kind of thing. So for example, since basically 0 is less than x less than pi by 2, x is between 0 and pi by 2, then sine x is a positive value. You know that in the first quadrant sine is a positive value. So now if I divide this equation, divide this inequality by sine x, which is a positive value, I'll get sine x by sine x is less than x divided by sine x is less than tan x divided by sine x. Otherwise, if x was a negative value, then this would become, for example, sine x by sine x is greater than x divided by sine x is greater than tan x divided by sine x. So it's really, really important to understand all of these things and actually use them. Otherwise, what you get after all of this process is most probably is going to be actually wrong. So now that is 1 is less than x divided by sine x is less than, now tan x by sine x is basically sine x by cos x divided by sine x, which is equal to sine x by cos x times 1 by sine x. Then you can cancel these two out and you'll get 1 divided by cos x. So that is 1 divided by cos x. And so now if I take the reciprocal of every basically part of this inequality, I'll get 1 is less than sine x by x. Sine x by x is less than cos x. Now what we wanted to prove here was a little bit different. Cos x is less than so over here we had by sine x we have 1 less than sine x by x less than 1, taking reciprocals throughout. So let me see. Oh, I made a mistake here. I'm sorry. I did make a mistake here. As I said, it's very tricky to work with inequalities because it's something that you usually don't work with. And well, see, when you take the reciprocal of for example something like this, what happens is that taking the reciprocal of 1 is, well, the reciprocal of 1 is 1. The reciprocal of basically x by sine x becomes sine x by x, and the reciprocal of 1 by cos x becomes cos x. Now since you've taken the reciprocal, then you have to, then less than becomes greater than, and again less than becomes greater than. Otherwise it would simply be wrong. Basically your inequality would not be right. So now if I rewrite this again from this side, so I get cos x is less than sine x by x is less than 1. And that is something that we can use in, and I mean that's what we wanted to prove. And that is what we can use in finding the limits of these trigonometric functions sine x and cos x. Now let's go over here and find the limits of two important trigonometric functions. Okay, so the next part that we have here has been called, basically it's been called Theorem 5. It's been called Theorem 5, and we have basically two important limits related to these trigonometric functions, which is, the first one is the limit of sine x by x as x tends to 0 is equal to 1, and also the limit of 1 minus cos x over x as x tends to 0 is equal to 0. So we want to basically prove these two limits. I mean, we want to prove that the limit of sine x by x is equal to 1, and the limit of 1 minus cos x over x is equal to 0. So we basically, what we just proved here, we said that basically cos x is less than sine x divided by x is less than 1. That means that this function sine x by x is basically sandwiched between the function cos x and the constant function 1, which takes the constant function which takes the value 1. This was what we just basically proved over here. Now and of course you know that the limit of cos x as x tends to 0 is equal to 1. The limit of cos x when x tends to 0 is equal to 1, because cos of 0 is equal to 1. And the theorem is complete by the sandwich theorem. So basically in the sandwich theorem, we said that if we had basically these two functions, we said that if basically we had basically three functions over here, we called it the sandwich theorem. We said that if f of x is less than or equal to g of x is less than or equal to h of x, then if the limit of f of x as x tends to a is equal to the limit of h of x as x tends to a is equal to L, then since this function is sandwiched between the two of these functions, then you can basically conclude that the limit of g of x as x tends to a is equal to L. So what that means is that, of course, you know that the limit of this function, this constant function, is equal to 1. So you can of course say that the limit of 1 when x tends to 0 is of course equal to 1. This is constant function. Whatever value x tends to, the limit is going to be equal to 1. So since this function is sandwiched between these two functions, based on the sandwich theorem, you can conclude that the limit of sine x by x, as x tends to 0, is equal to 1. That is basically the first part that we wanted to prove here. Now the second part, is basically this. We want to prove that the limit of 1 minus cos x over x, the limit of 1 minus cos x over x as x tends to 0 is 0. As x tends to 0 is equal to 0. Okay, so there is some trigonometric identity that we have had before. I don't know, I haven't done these identities here on YouTube, of course, but of course nonetheless the trigonometric identity is there. So you know that basically these two trigonometric identities are pretty useful trigonometric identities, and they keep coming up everywhere, all over the place, and you do need to learn them. So first of all, basically sine 2x is equal to 2 times sine x cos x. Sine 2x is equal to 2 times sine x cos x is equal to 2 times tan x over 1 plus tan squared x. 1 plus tan squared x. So this is sine 2x. Now cos 2x is equal to cos squared x minus sine squared x. That it is also equal to 2 cos squared x minus 1. 2 cos squared x minus 1. It is also equal to 1 minus 2 times sine squared x. 1 minus 2 times sine squared x. It is also equal to 1 minus tan squared x. 1 minus tan squared x over 1 plus tan squared x. So that is basically cos of 2x. Cos squared x minus sine squared x. 2 cos squared x minus 1, 1 minus 2 sine squared x, and this thing over here as well. Now, if you have, so basically based on this part over here, you can say that cos of 2x is equal to 2 cos squared x minus 1. And if you write this as 2 sine squared x, I'm sorry, based on this part, not this part, but this part. So you can say that basically cos of 2x is equal to 1 minus 2 times sine squared x. So 1 minus 2 times sine squared x. So what that means is that then the cos, if you can write this as cos of instead of x, instead of 2x, if you write x, that becomes 1 minus 2 times sine squared. Half of this angle is x divided by 2, and then take this one to the other side. You will get cos x minus 1 is equal to negative 2 sine squared x divided by 2, and then multiply both sides by negative 1. You'll get 1 minus cos x is equal to 2 sine squared x divided by 2. So that means that 1 minus cos x, you can write it as 2 sine squared x divided by 2. Okay. So what that means is that you can write, instead of limit of 1 minus cos x by x, so limit of 1 minus cos x by x, when x tends to 0, you can write it as the limit of 1 minus cos x, you can write it as 2 sine squared x divided by 2. divided by x as x tends to 0, and then you can write this as the limit of basically well, you can write this as sine x divided by 2 times sine x divided by 2, because you have basically sine squared x divided by 2, and this is 2 divided by x. So 2 divided by x, you can write it as 1 over x divided by 2. So I write this 2 divided by x, I bring it to the denominator, so that means that I write it as x divided by 2, as x tends to 0. And so what that means is that now I can write this as, this is the whole limit of this whole thing, so I can write it as the limit of sine x divided by 2 over x divided by 2 when x tends to 0 times the limit of sine x divided by 2 as x tends to 0. Now we said that over here, we showed that somewhere over here, hopefully I can find it, we showed that the limit of sine x by x when x tends to 0 is equal to 1. We showed that the limit of sine, we showed that the limit of sine x by x when x tends to 0, this is equal to 1. Now of course you might be concerned about the fact that this is x divided by 2, but over here as x tends to 0, of course x divided by 2 also tends to 0. So then you can basically use the same theorem that we had over here to write this part as 1. And the limit of x divided by 2 when x tends to 0, you can take it as the limit of sine x, when x tends to 0, which is equal to 0. So this is equal to 0, and so this is equal to 0. So then what that means is that the limit of 1 minus cos x over x as x tends to 0 is equal to 0. This is that, and the first part that we showed in this theorem was that the limit of sine x by x as x tends to 0 is equal to 1. These are the two parts of this theorem proved, and you can use it in the rest of this part. Now there are some parts over here that you might be concerned about. I will show you basically them in the, I'll show you all of these parts in the rest of the discussion here. Now I have a couple of things here to discuss. Okay, so now let's evaluate some basically two limits. Suppose that you have, for example, the limit of basically sine 4x over sine 2x when x tends to 0. Okay, so I made a mistake over here. Let me clear this out. So basically we said that the limit of sine x over the limit of sine x over x when x tends to 0 is equal to 1. We showed this, we proved this over here. Now I can rewrite this as the limit of, basically sine 4x. I can write this as the limit of sine 4x over 4x, for example, and sine 2x over 2x. And now I have, basically in the numerator I have 4x, and in the denominator over here I have 2x. I have 2, meaning that I have divided the numerator by 4x, divided the denominator by 2x. So they are not the same things. So I have to divide the denominator by another 2 so that both of them are 4x. And then as x tends to 0 here, I can write this as the limit of sine 4x over 4x as x tends to 0 over limit of sine 2x over 2x, 2 times 2x when x tends to 0, and then I can take this 2 out, meaning that this is a 1 by 2 actually, it's in the denominator, so this is a 1 by 2. This is the same thing as the limit of basically sine 2x over 2x, and then you have a basically times basically 1 by 2, right? So you have you're taking the limit of this, and as x tends to 0. So this is a constant function, you can take it out, meaning that you can write it as 1/2 the limit of sine 2x over 2x as x tends to 0. Now, so since then this 1/2 is in the denominator, it's the same thing as 1 over 1/2. So 1 over 1/2 is equal to 2. So this becomes 2 and goes to the numerator. So I can write this as 2 times the limit of sine 4x over 4x as x tends to 0 over the limit of sine 2x over 2x as x tends to 0. And now this 2 is basically up here. So now the limit of sine 4x over 4x. So now in order to evaluate these two limits, now you see that over here we said that the limit of sine x over x when x tends to 0 is equal to 1. Over here I have the limit of sine 4x over 4x as x tends to 0 is equal, and I want to evaluate this. So when things get a little bit confusing like this, and you want to decide, for example, what you need to do based on for example some case like this, what you can do is that, for example, this part you can write it as the limit of sine 4x over 4x as x tends to 0. We want to calculate this limit. So what you can do is that you can substitute basically 4x with, for example, y or some other variable, meaning that y is equal to 4x. So if y is equal to 4x, then x is going to be equal to x is going to be equal to, divide both sides of this equation by 4, and you will get y divided by 4 is equal to x. Or actually you don't really need to do that. So here you have basically you can write 4x as y basically. So you will have the limit of sine y, so you can write this as the limit of sine y over y, and then as x tends to 0, of course, then y tends to 0. As x tends to 0, then y tends to 0, because if x tends to 0 over here, y of course tends to 0, because they have a direct relationship. So what that means is that, but of course you need to be careful in these cases. For example, suppose that you had this expression over here was 4 over x, for example. Now if you take, for example, if you take 4 over x as y, okay, and if basically in your limit x tends to 0, then as x tends to 0, then of course y tends to infinity, as you know, because as x gets smaller and smaller, y gets bigger and bigger, because this is in the denominator, this is in the numerator. They have an inverse relationship. So for example, in this case, you would solve the problem this way, but over here they have a direct relationship, and you could solve the problem very easily that way, meaning that as x tends to 0, then of course y tends to 0, and then you can write this as, basically instead of x tends to 0, you could simply write y tends to 0. And so that's basically the same thing that we had over here. So only the variable has changed, meaning that the limit of sine y over y as y tends to 0, this is simply equal to 1. So then what that means is that this part over here is equal to 2 times 1, and with the same logic this part is also 1, so this is equal to 2. This is equal to 2. So as another example, let's say that you have the limit of, for example, tan x over x. Let's say that you have the limit of tan x over x as x tends to 0. Extending to 0. So you can write this as the limit of, basically tan x is sine x over cos x, so you can write this as x times cos x, and x tends to 0. Now you can write this as the limit of sine x over x, with this over here, times cos x as x tends to 0. And then you can write this as the limit of sine x over x as x tends to 0. Now the problem occurs when you have this x in the denominator and your x tends to 0, and so that makes taking the limit a little bit difficult. Otherwise, for example, if you have the limit of, for example, cos x as x tends to 0, that's very simple. You could you would simply evaluate the value of this function at x is equal to 0, which is equal to 1, for example, and so this part, you know, it is equal to 1. But when you have, for example, the limit of basically cos x, for example, by x, when x tends to 0, then in this case, then you can see that the variable is also in the denominator, and in the denominator, x tending to 0 makes things impossible for taking the limit. And so then we have to come up with these ways of basically finding some, for example, some sort of equation or formula for particular situations. And then when you have a situation like this, you have to somehow rearrange your problem so that, for example, one part of the problem becomes something like the one that we found over here, and then substitute and solve the problem. Okay, so what that means is that now I can write this as the limit of sine x over x as x tends to 0 times the limit of cos x as x tends to 0, which is equal to, well, this part over here is equal to 1, and this part over here is equal to 1, so this is equal to 1. And here there is a part about taking limits that is actually a kind of a conclusion about all the things that we have done so far. Okay, so the basically, as a general rule, we can say that when you're evaluating the limit of some function, well, there is a whole lot of mosquitoes in here, so every now and then I have to deal with them. So it says that given that the limit, so suppose that you want to evaluate some limit, for example, the limit of some function f of x by another function g of x, as x, for example, tends to some a, for example. Okay, suppose that I want to evaluate this limit. Now, of course, limit of the limit of some function the limit of some function f of x as x tends to a. This is easy. This is, in all cases, it's going to be a polynomial. Polynomial in the form, for example, a of 0 plus a of 1 x raised to the power 1, a of 2 x raised to the power 2 plus all the way up to a of n a x raised to the power n. This is called a polynomial. So whatever sort of expression that you have in, I would say, in all of mathematics, is going to have some sort of variable and some sort of degree, and that's basically, that simply is a polynomial. For example, suppose that you want to find the limit of x as x tends to, for example, 2, as x tends to 0 or whatever. So this is a polynomial. Suppose that you want to find the limit of, for example, x squared plus x as x tends to, for example, some a. This is again a polynomial. Suppose that you want to find the limit of x cubed plus x squared plus 3x plus 5 as x tends to some a, for example. This is again a polynomial. And we know how to find the limit of polynomials. We said that the limit of f of x, if f of x is a polynomial as x tends to a, is equal to f of a. Very simple, very easy. And And of course, if you have if your polynomial, if the function that you want to take the limit of is a rational function, if f of x is equal to, for example, g of x by h of x, this would be called a rational function. A rational function. A rational function simply because it's a ratio of two polynomials. And since we know how to take the limit of two polynomials, then we found some way to find the limit of a rational functions, because we can find the limit of the numerator, we can find the limit of the denominator, and both of them are basically polynomials, so we have no problem there. Now, the problem arises in some cases where you get a 0 in the denominator, and that is basically like this. For example, you have, of course, we are going to solve a couple of problems after, in the next video, and we will talk about all of these cases extensively. But for the sake of this explanation, let's say that you want to find the limit of f of x by g of x as x tends to a. So this is a rational function. Now suppose that provided that the limit exists, sometimes the limit does not exist, meaning that you get, for example, you get your limit in the form 4 divided, or some number divided by 0, in which case the limit does not exist. The limit does not exist. So if you get to this form over here, some number a divided by 0, then you can simply say that the limit does not exist, and then you have to simply abort the process, meaning that you have to just simply stop there, and the limit does not exist. But if the limit does exist, you usually get your limit in the form, for example, 0 by 0, and then the limiting process will take care of the problem of basically dividing 0 by 0, and that's basically the art of the limiting process, really. That's the main thing that the limiting process does for you. It solves the problem of dividing 0 by 0, which is normally, well, of course not possible, but the limit somehow magically does it for you. So what that means is that now, provided that this limit exists and you want to evaluate this limit, first you check the value of f of a, because this is a polynomial. And then you check the value of g of a, since this is also a polynomial. Suppose that basically both are 0. Both are 0. If both are 0, then we need to find out. Then we need to find the factor. Then we need to find the factor making them 0, and eliminate that. Eliminate that factor. So then if there is a factor in the numerator and denominator that is making them 0, you can simply find that factor, cancel them out, and now since that factor is gone, then now they're not going to be equal to 0, and then that will give you will get some value for the limit of f of x by g of x. Meaning that in this step, you will write your f of x as, for example, some f1 of x times some f2 of x, and you can write your g of x, meaning two different functions, two different polynomials multiplied together. You can write your g of x as g1 of x times g2 of x. And here basically, for example, suppose that f1 of x is equal to 0, and over here suppose that, for example, g1 of x is equal to 0, and over here you will get your you will basically do this process in such a way that your f1 of x is equal to 0, but f2 of x is not equal to 0. Again, here g1 of x is equal to 0, g2 of x is not equal to 0. Then usually what you can do, you will cancel these two out from the numerator and denominator, and then you can write your limit as the limit of basically f2 of x over g2 of x over g2 of x as x tends to a, and then you can find the limit. So then what that means is that then if I take we can rewrite this basically as they have written over here. They have written f of x by g of x. Once you cancel out those factors that is making them 0, you can write them. You can write this as p of x over q of x. P of x over q of x, where basically q of x is not equal to 0. And then the limit of f of x by g of x as x tends to a is equal to the limit of this thing over here, p of x over q of x as x tends to 0, or x tends to a basically, for example, x tends to a, which is then equal to p of a over q of a. Very simple. P of a over q of a, and that is the value of your limit. So it's basically not a very complicated process. It's a very simple process. Once you understand it, you're basically and of course we have all of these exercises, and that's basically a lot of exercises, really, like 28, many of them, 32 exercises we have, and we will go through each one of them and we will solve them, and in each case I will hopefully explain each and every one of them, and we will understand this concept properly. So I'll see you in the next video. Thank you.